Welcome to the Unit 0 Section 1 video on number sets. We're going to be working with numbers a lot in this course, obviously being a math course, so we need to know how to use these numbers and how to classify the numbers that we will be using. So we're going to start off by talking about the real number system. Now, the real number system is a system that classifies all the real numbers literally that exist in the world, okay? So any number that you can physically measure or you can physically put a value to is a real number, okay? And most of the numbers that you've worked with, in fact, probably all the numbers you've worked with in your life up to this point have been real numbers. Now, we can classify real numbers into two different groups. We can call them rational numbers or irrational numbers. So let's start off by talking about rational numbers. These are the numbers that can be written as a fraction. Now, where does the word rational come from? Think about the first part of that word. It's ratio, okay? What is a ratio? It is a fraction. 3 to 1, 2 to 1, okay? So that is where the word rational comes from, and the word rational means it can be written as a fraction. This includes decimals that terminate and repeat, okay? So, for example, 0.5 is a decimal that terminates. You know that 0.5 can be written as the fraction 1/2. Now, what about a decimal that repeats? How about 0.33333 forever? You know that can be written as 1/3, okay? So, decimals that terminate and repeat are rational numbers because they represent decimals that represent fractions. Now, integers are a subset of rational numbers, okay? So integers are basically rational numbers that have a denominator of 1, okay? So take a look at these examples. We've got -2, -1, 0, 1, 2. You can write all of those as -2/1. -1/1, 0/1, 1/1, 2/1, okay? They can still all be written as fractions, but we don't have to have the over 1 part of it. We don't need that denominator of 1 to be written to understand that what the value of that number is, okay? So that's what an integer is. It's basically a rational number with a denominator of 1. Now, we can break down integers into whole numbers. Whole numbers are a subset of your integers. They're basically all of your integers that are not negative. So that includes 0, 0, 1, 2, 3, 4. And then we can take this down to another subset called natural numbers. Natural numbers are a subset of whole numbers and are your counting numbers. So basically all of your whole numbers except for the number 0. So that's a breakdown of rational numbers. We have all these different subsets of rational numbers. Now let's talk about irrational numbers. These are numbers that cannot be written as a fraction. These are decimals that do not terminate or repeat. So probably the most known one that you probably are familiar with is the number pi. You know that pi is 3.14, but it doesn't end there. That's a rounding of that number. It goes on to 3.1415, so on and so forth, and it never repeats, or at least we've never gotten pi out to so many digits past the decimal that we know that it repeats, okay? So pi is an irrational number. Sets of numbers are often represented by figures called Venn diagrams, okay? You are probably familiar with Venn diagrams where you've taken one circle and another circle and have them overlap in the middle to show the parts that you have in common. The size and the shape of a Venn diagram are unimportant. However, usually a rectangle is used to represent the universal set, and circles or ovals are used to represent the subsets of the universal set. So I'm going to show you a picture so you have an example of this. So let's take a look at the set of real numbers. This is my universal set for what we're talking about here. Okay? All real numbers can be divided into irrational numbers and rational numbers. Those are our two classifications of real numbers. Now, within the rational numbers, we can have a subset of integers. Okay? Remember, integers are all your rational numbers that have a denominator of 1. Within the integers, we have the whole numbers. So the whole numbers are all the integers except for those that are negative. And then within the whole numbers, we have the natural numbers, which are your counting numbers. So that's all your whole numbers except 0. So as we get deeper and deeper into the center of this, we are leaving out more and more numbers. Notice that all of the natural numbers are whole numbers. Okay, so 1, 2, 3, 4 are not only natural numbers, but they're also whole numbers. All the whole numbers are integers. So 0, 1, 2, 3, 4 are not only whole numbers, but they are also integers, which is the circle around that. And then all integers are rational numbers. So -2, -1, 0, 1, 2, 3, these are all rational numbers. Okay, so you can classify certain numbers as more than one type of number. So let's do a couple of examples. The first one, we're going to use that diagram, and we're just going to place each of these numbers into the most specific area of the diagram. Okay, what is the most specific way that we can describe these numbers? So let's start off with -5. Now, -5, of course, is real, but we can also classify as either irrational or rational. We know it's rational, so now is it also an integer? -5 is an integer, so then we go deeper than that. Is -5 a whole number? And it is not a whole number. So therefore, the most specific area of the diagram we can place -5 is in with the integers. Now going on to 0, we know that 0 is real. We know that it is a rational number. We know it's an integer. We also know it's a whole number, but it is not a natural number. So the most specific place we can place 0 is a whole number. Now, the negative square root of 10. Let's think about this one. Where can we place negative square root of 10? Well, first of all, is it irrational or is it rational? If you were to put the square root of 10 in your calculator and see what the decimal value is for it, you would see a decimal number that does not appear to repeat or terminate. So, therefore, the square root of 10 is actually an irrational number, and making it negative still keeps it irrational. So, therefore, we have an irrational number. -8/17. Well, that's obviously rational because it's a fraction, but it is not an integer because the denominator is not 1. So therefore, we're going to place that in our rational numbers. 8 is rational. It's an integer because the denominator can be 1. It is a whole number, and it is natural because it's not 0. -12 is rational. It's an integer, but it's not a whole number because it's negative. The cube root of 2. This is another one that you're going to put in your calculator, see what the decimal value is, and the decimal appears to not terminate or repeat, so therefore it's irrational. 2/3 is a fraction. The denominator is not 1, so it's rational, but it's not an integer, so we'll put it in the rational category. -3 is rational. It's an integer, but it is not a whole number because it's negative, so we're going to put that in integers. 154. It's rational. The denominator is 1, so it's an integer. It is a whole number because it's not negative, and it's natural because it's not 0. And then finally, pi, we discussed this one. It is an irrational number. All right, let's take a look at another example. This time, we're going to just identify all the sets to which each number belongs. Okay? So, first of all, 12. It is a real number. It exists in the real world. Is it rational or irrational? Well, it is rational. It is an integer. It is a whole number. And it is natural. Okay? Because it is a counting number, right? 1, 2, 3, 4, 5, 6, 7, 8, on through all the counting numbers. So it is natural. So that is all the ways that we can classify this set or this number. All right, for B, -5. We know it's real, we know it's rational, and we know that it's an integer. But because it's negative, it is not a whole number. So that's as far as we can take it. All right, for C, we have 0.3. And remember, when you have a line over a number after the decimal, that indicates that this number is repeating. So this means 0.33333 forever. Well, we know that that's a real number. All these numbers are going to be real numbers, by the way. We know that it is rational because 0.333 forever can be expressed as the fraction 1/3. But we know it's not an integer because it is not a fraction with a denominator of 1. All right, for D, we have 0. 0 is real. 0 is rational. 0 is an integer. It is also a whole number, but it is not natural because 0 is not part of the natural numbers. 0 is not considered a counting number. All right, for E, we've got 2.449489, and the 3 dots can indicate that it continues forever, but it doesn't necessarily continue forever repeating. So therefore, we have a real number, but it is irrational because it is a decimal that does not repeat forever. For F, we have square root of 4. Now be careful with this, okay? Because we've seen that square roots tend to give us irrational numbers. We know it's real, but think about what the square root of 4 is. What's the square root of 4? Is there anything times itself that gives you 4? Well, yes. 2 times 2 gives you 4. So therefore, the square root of 4 is 2. And 2, we know, is rational. That is an integer. It's whole. And 2 is also a counting number, so it's natural. All right, for G, we have 5/3. That's a fraction, so it's real and it's rational. But the denominator is not 1, so therefore, that's as far as we can go. It's not an integer. And if it's not an integer, it's not whole. And if it's not an integer, it's also not natural. Okay? And then finally, for H, pi is our classic example of a real irrational number. So we talked about real numbers being classified as rational or irrational numbers. Now let's talk about what happens when you perform some sort of operation like addition or multiplication to two rational numbers, two irrational numbers, or a rational and irrational number, and see what kind of number do we get out of it. So it can be helpful to identify the type of solution that occurs when numbers are added and multiplied. So here's a little table that we're going to use to identify what happens when we add or multiply numbers. Remember, sum is the result of numbers that you add together, and the product is the result of numbers that you multiply together. So let's start with rational and rational numbers. Two rational numbers, two numbers that can be expressed as a fraction. When you add them together, you're always going to get a rational number as a result. Okay? So two fractions added together are going to give you a fraction of some sort. Okay? Even if that fraction is over 1, the denominator is 1, it can still be considered a fraction. Okay, that's what makes it rational. Now, what if we were to multiply two rational numbers? Well, multiply two things that are fractions together, and you're still always going to get a rational number out of it. Okay, so it's fairly simple. If you have two rational numbers, you add them together, you get a rational result. You multiply them together, you also get a rational result. Now, what happens if you take two irrational numbers and you add them? Or you take two irrational numbers and you multiply them? So let's talk about the sum first. Well, it gets a little bit tricky. Two irrational numbers added together are always irrational, except if you have the positive and negative version of the same number. For example, if you have positive pi and negative pi, and you add those together, what's your result? Well, you get 0, right? 0 is not an irrational number. So you're going to have an irrational result unless you have the positive and negative version of the same number being added together. Now, what about the product? It's always irrational unless you have the square root of the same integer. Okay, so what does that mean? Well, what if you have the square root of 4 times the square root of 4? Well, that's maybe not a good example because we know the square root of 4 is 2, so 2 times 2 is 4. Let's try something that is not going to be rational when we take the square root. How about the square root of 7? The square root of 7 is irrational. You put it in your calculator, you're going to get a decimal that goes on forever and doesn't repeat. If you do the square root of 7 times the square root of 7, you're squaring the square root, which means that you are basically canceling the square root out, and you're left with 7. If you were to put square root of 7 times the square root of 7 into your calculator, you would see that the result is just 7. And 7 is rational. So if you have the square root of the same integer being multiplied on itself, then you're going to get a rational result instead of irrational. Otherwise, it will be irrational. Now, what if you take an irrational number and add it to an irrational number? Well, you're always going to have an irrational number. If you take pi, which is 3.1415 going on forever, and you add 3 to it, then you're just going to end up with 6.1415 going on forever. It's still going to be irrational. Okay? What about if you multiply a rational and irrational number together? It's always irrational unless you're multiplying by 0, because anything times 0 is 0, and 0 is not irrational. It's rational. Okay? So when you multiply an irrational number times anything, it's always going to be irrational unless you're multiplying a square root by itself or you're multiplying by 0. So I know that's a lot of information. I know it may not be the most straightforward information yet, but I think it'll make more sense when we do a few examples. So let's determine whether each sum, difference, or product is a rational or irrational number. You notice I threw in differences here. A difference is the same as a sum, except we have a negative in there. Okay, so for example, with A here, we could rewrite 1/3 minus 3/4 as 1/3 plus negative 3/4. Okay, so in this example, both of these numbers are rational. And when you add, or in this case subtract, two rational numbers, you're going to get a rational number as a result. All right, for B, we have 5 times the square root of 12. Square root of 12 is irrational. 5 is not 0, so 5 times an irrational number is going to give us an irrational number. 22 plus 0.02, well, that's a decimal that terminates. So it could be written as a fraction, and so we have a rational number plus a rational number, so our result's going to be rational. For D, we have the square root of 21 minus 2. Square root of 21 is irrational. And if you subtract 2, you're still going to have an irrational number because the part after the decimal is not going to change. So we still have an irrational number here. All right, square root of 144 times the square root of 289. Well, we know from our multiplication tables that the square root of 144 is 12, so that's a rational number. How about the square root of 289? Well, if we put that in our calculator, we find that that's actually a perfect square. It's 17. So we have 12 times 17. We have a rational number times a rational number, and we know that's going to give us a rational number as a result. Now for F, square root of 2 is irrational, but we're also multiplying it by itself. The square root of 2 times the square root of 2 is going to give us 2 as a result. You can do that in your calculator and see that for yourself. So 2 is definitely a rational number, so we have a rational result here. 5.7 is a rational number that can be expressed as a fraction. 4/7 is a rational number because it is a fraction. So a rational times a rational gives us a rational as a result. And then finally, pi plus 5. We talked about this already. You add 5 to 3.1415 repeating forever, or not repeating, I should say, just the decimals going on forever. Then you are left with 8.1415. decimal going on forever, so it stays irrational. Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.